Hello, welcome. In this video, we're looking at question 4, and we want to solve for the value of x in each diagram. So what I want to do is just apply the theorems and kind of name them for you, say some of the basic logic, but you do want to understand why these things work. I have other videos for them, but you can also look them up really anywhere. But it's important you understand what's going on here. So in the first one, this is the angle bisector theorem that we're going to apply. And what you might notice is that this segment right here is an angle bisector. And when that happens, and you're given the information you've seen here, there are ratios that you could write to solve the problem. The way I like to view it is that the ratio of 5 to 10, so 5 to 10, is going to be equal to the ratio of x, so that kind of other half of the side across the angle bisector is forming the numerator in this case, and then over 6. This is an equal proportion. And you could view that in different ways if you swap the proportion around. So, for example, you could say x to 5 is equal to 8 to 10. So people like to write it that way. Write it in whatever arrangement works for you, but this is the basic structure. So that being said, let me move this over. No, that's the image. Let me move the problem over here. And I don't think we need to show all the rearrangements. I'm just going to show other common ones. You could write x to 5 equals 6 to 10. Right? You could write that one around. You could also take reciprocals here. You can say 10 to 6, right, is the same ratio as 5 to x. These are all equivalent things, and so on and so forth. So I just wanted to establish there's some flexibility there. I chose this one. It's kind of like how I enjoy seeing it this way, but also puts x in the numerator. If I multiply both sides by 6, 5 times 6 is 30 over 10, and x is equal to 3. And then, look at the diagram, see if that's reasonable. It looks like a reasonable measurement, right? Nothing absurd here. And the diagrams aren't necessarily to scale, but if you get something like 100, right, that would be not very reasonable. And certainly if you look at this shape right here, it is a triangle, right? So 6 plus 7 is 13. As you might know, the triangle equality says, well, basically if I start here and I go 6 this way and 7 that way, and that's 13, there's no way that x could also be 13. In fact, it has to be less than 13, which is a number that we got. Okay, let's go to part B. So in part B over here, I have some old writing from a different video. Let me just clear that off. Again, we're trying to solve for x, and I think for me in this case, I'm realizing that we've got these 3 right angles, which means that we have these 3 lines here that are all perpendicular to the same line, so they're all parallel with each other. And we can use what's called the partition postulate. And what this tells me is that the ratio of these segments 2 and 3 over here, so 2 to 3, is equivalent to x. And this little segment right here is going to be 8 minus x. So I could set it up this way and try to solve it. What else could I do? I could say on the left, 2 to 5, for example, is equivalent to x to 8. And that's actually a lot easier to solve in this case, but we'll solve both just for fun. So let's do the bottom one first. If I multiply both sides by 8, I get 16 over 5. And on the right, x divided by 8 times 8 is just x, and that's our answer for x. But if we do solve it this way, we should get the same answer. It's a true statement. So I'm going to kind of exploit the fact that the product of the means is the product of the extremes. So 2 times 8 minus x has to be equal to 3 times x. So 2 times 8 minus x is going to be 16 minus 2x equals 3x. And if we add 2x to both sides, we get 16 equals 5x. And then divide by 5, and notice we get the exact same thing. So we can actually partition those segments in different ways and get the same answer. That's the partition postulate. That's using parallel lines and partitions, and then the angle bisector theorem is before that. Okay, C. I like C because I find it particularly challenging. So this is one where I definitely kind of draw out what's happening. It doesn't seem right away that there's any particular theorem that I could use, but there's probably a way to reorient these things to show similarity. So like in this triangle right here, I notice that we've got a right angle, and I'm going to call this location, let's just name it A. So at A, there's this angle that our triangle has there. And then I also notice for this bigger triangle, it also shares a right angle, and it also shares the angle at A. So I want to use that because those two triangles both have right angles and they share that common angle A. So by angle similarity, I know I've got similar triangles. So I still find that hard to draw, so I'm going to do that slowly. My purple triangle is smaller. I'm going to draw that first. There's my right angle, and like here's the peak of angle A. So this is the length of X, and the hypotenuse is 8. Okay, got that. Now I'm going to go to the green triangle, which is larger. I know I can orient it in the same way, so I'm just going to kind of draw that out first, put my right angle there, and it's not to scale. But if I look at the picture, going from the right angle to A, I've got 4 plus 8, I've got 12. And the hypotenuse is going to be 6 plus X. Now they both share this angle A up top. So by angle similarity, they are similar to each other by angle similarity. And also get an interesting smiley face that I just drew. That says angle similarity. So what does that mean? Well, the ratio between corresponding sides is going to be proportional. So for example, I could write x to 8 equals 12 to 6 plus x. That's a ratio I could write. That seems pretty useful. We can do that. I could also write in other ways. I could say x to 12, so like the leg over here to the leg here is going to be equal to the ratio of one hypotenuse to the other. And if you look at that, it's the same ratio as I just wrote, but just I swapped two numbers. I swapped the 8 and the 12, which algebraically you can do. Okay, but let's solve this because I don't have enough room here, I think, to solve this. So I'm going to write x over 8, do a new page, equals 12 over, let me go back real quick, over 6 plus x. All right, so what am I going to do? Product of the means, that's these two numbers, equals the product of the extremes right here. The extremes are x times 6 plus x, so I'm going to write that down with parentheses, and then 8 times 12 is 96. On the left, I got to distribute. I've got 6x plus x squared equals 96, and I've got a quadratic, so I'm going to factor. I'm going to bring everything over and try to factor. X squared plus 6x plus 96 equals 0. Now, before I try and factor, I like to think of the discriminant. This helps me figure out and get some bearings. Like, is there going to be a rational solution to this thing? So it's going to be b squared, which is actually 6 squared. That's the b value, right? The coefficient of x, minus 4 times 1 times 96. So that's 36 minus, oh, wait, I made a mistake. This should be negative. It should be minus 96 right there, which means it's 4 times negative 96 or plus. So what's that? So 4 times 90 is 360. 360 plus 24 is 384. And I've got 384 plus 36. So 380 plus 20 is 400. 416, I have 420. Now 420 is not a perfect square. So if I was finding the x values here and I was to use the quadratic formula, I would take the square root of this, right, and try to evaluate it. But the square root of 420 is irrational. So that tells me that there's no friendly way to factor this with with rational numbers. So x is going to be equal to negative 6 plus or minus the square root of 420 over 2. So how can we break that down? I'm going to divide both numbers on top by 2. Now that might seem daunting at first, but negative 6 divided by 2 is negative 3. Plus or minus the square root of 420, we can think of dividing that by the square root of 4. Same thing as 2. And when you have two square roots, you can divide them directly. I know 420 divided by 4 is 105. So this is going to be negative 3 plus or minus the square root of 105. And 105, I don't think can be rationalized or broken down any further. Not rationalized. So 5 times 21 is 105. And 21 has factors of 3 and 7. So none of these factors are perfect squares. So this is actually our x value that solves that diagram. Okay, we've got one left here. So in this one, we've got two similar triangles. If you look, let's say we have A, B, C. This triangle has the angle up top at A, and then if I look at another triangle, let's call it A, D, E. Sorry. ADE also has the angle at A, so they both share the same angle. But also, we're given that they share these other angles. The angle ADE and ABC are congruent. So it also means we have these parallel lines right here, but more importantly for us, triangle ADE is similar to triangle ABC. So we can use it to set up a proportion here. I'll say 6 to 2x minus 7, and that's just looking at this length to this length is going to be congruent to this whole length here, 6 plus x to 2x plus 3. So 6 plus x to 2x plus 3, and we've got a proportion that we want to solve. Let's solve that on a blank template here. So we have 6 over 2x minus 7 is going to be equal, let me go back, 6 plus x over 2x plus 3, 2x plus 3. So the product of the means is the product of the extremes. So the means are these two, and the extremes are those two. So we want to multiply them. Let's do our extremes first. So we have 6 times 2x plus 3. And then we have our means. So we have to do just some distribution here. 2x minus 7 times 6 plus x. So on the left, we're going to have 6 times 2x, that's 12x. And then 6 times 3, that's 18. On the right, you get 2x times 6, which is 12x. 2x times x, which is 2x squared. Negative 7 times 6, which is negative 42. And then negative 7 times x, which is negative 7x. And I notice here, we're going to try to do some cancellation to get this working out. Looking across, oh, this is pretty cool. The 12x's cancel. And I'm going to subtract 18 on both sides. So 0 is going to equal 2x squared minus 7x minus 42 minus 18 is minus 60. And then we want to factor this thing. So, okay, what can we do? We're going to use 2x and x for the 2x squared, right? And then there's a lot of factors for 60, and we need to get to 7. So I'm going to start listing some of them out. I don't think I'm going to end up using 60 times 1. I'm going to probably use like 4 and 15, maybe. And then, I don't know, 20 and 3. So I'll start with those. So I noticed that if I double, because I know that the 2 is split into two factors of 2 and 1. So in the distribution, one of the factors of 2 and 1, is going to be multiplied by one of the factors of 60. So I'm imagining if I double 4, that's 8. And then I multiply the 1, so 2 times 4 is 8. And then I know 1 times 15 is 15, and those are 7 apart. 2 and 4 is 8, that's 7 apart from 15. So I'm going to use some combination of that. So 2 and 4 are going to be multiplied, and then 1 and 15 are going to be multiplied. And we need to make a negative product. So I'm going to make the signs opposite. And this, I'm going to test it real quick. 2x squared plus 8x, 2x squared plus 8x, minus 15x minus 60, minus 15x minus 60, and that works. We have the minus 7 in the middle. We're in a good spot. So now we just want to solve for x. So let's see what our options are. So this tells me x could be negative 4, which I'm going to reject because it doesn't fit the diagram. And also x could be 15 over 2. And that seems to be a reasonable measurement. So I'm going to reject the -4, and keep 15 over 2. All right, I hope this helped.